Welcome to the Deep Dive. Today we're tackling a huge topic, one that, well, underpins almost everything else we talk about in science and technology. Materials science.
It really does. It's kind of the science of stuff, isn't it? What things are made of, why they behave the way they do. We're talking solids, mostly, but sometimes liquids, even gases used for specific jobs.
Exactly. The science of what everything is made of. And our mission today, using the great sources you pulled together, is to give you a really solid, fast-paced overview. Core concepts, the history, where it's all heading.
Yeah, we want you to walk away understanding the language, how material scientists think about creating something new or improving something old. It's fundamental to, well, all engineering.
Okay, first things first. There's material science and materials engineering. They sound similar, but there's a key difference, right?
Absolutely. Think of material science as the deep dive, the research part.
Yeah.
Understanding why a material has certain properties, looking at its atoms, its structure, the fundamental knowledge.
In engineering.
That's the application side. Taking that science and figuring out, okay, how do we use this? How do we make it reliably, cheaply for a specific product or industry? They absolutely have to work hand in hand.
Got it. And there's a central concept, almost like a mantra for the field. We called it the materials paradigm.
Yes, the materials paradigm. It's crucial. It's this chain. Processing leads to structure, which determines the properties, which then dictates the final performance.
Processing, right arrow structure, right arrow properties, right arrow performance.
Okay. Change any step, and you change what comes after, especially that first step, processing. How you make it defines everything else. It's the lever you pull.
And this isn't just like a modern lab idea. This relationship, this paradigm, explains why history unfolded the way it did, doesn't it? You look at the Bronze Age, the Iron Age.
Precisely. Moving from one age to the next wasn't just finding a new rock. It was about mastering a new process that allowed control over the material structure, giving you better properties, maybe harder or stronger or easier to shape, which led to better performance in tools, weapons, everything. It's that constant cycle.
So let's dig into those roots. Where did this thinking actually start? It feels modern, but people have been working with materials forever. Pottery, metal.
Oh, forever. The practical knowledge is ancient, absolutely. Trial and error, observation, add this, heat it like that, you get bronze. But the intellectual framework, that really comes out of the Age of Enlightenment.
Right, applying systematic thought.
Exactly. People started using the tools of early chemistry, physics, mechanics to figure out the why behind those old observations in metallurgy and mineralogy. Not just that it worked, but how it worked at a deeper level.
And as you said, those breakthroughs define eras. Stone, bronze, iron, steel. Each leap forward was about better processing, wasn't it? Controlling heat, purity.
Completely. Getting copper and tin pure enough, learning the right ratio for bronze, then figuring out how to get iron hot enough to work it, and later, crucially, learning to control the carbon content to make steel. Each step was a processing triumph, leading to superior properties.
Was there a key theoretical moment that really kicked off the modern field?
I'd point to Josiah Willard Gibbs, the American scientist, late 19th century. His work on thermodynamics was just revolutionary for this.
Thermodynamics, like heat and energy, how does that connect?
Gibbs showed that thermodynamic properties, things related to energy and stability at the atomic level, are directly linked to the physical properties you observe, like strength or melting point. He provided the mathematical tools to predict which material structures or phases were stable under certain conditions. It connected the microscopic world to the macroscopic world.
Okay, so the theory was developing. But when did material science become its own field, separate from, say, metallurgy or chemistry?
That really happened after World War II, sort of in the 1940s and 50s. The field exploded beyond just metals and ceramics. Suddenly, you had intense research into polymers, semiconductors, biomaterials, a completely new classes of stuff.
What drove that expansion?
A big part of it, at least in the U.S., was government funding, specifically from ARPA, the Advanced Research Projects Agency, now DARPA. In the early 60s, ARPA funded these interdisciplinary materials research labs at universities.
And the goal wasn't just basic science.
No, the goal was explicitly to push the boundaries, to design new materials for specific needs, especially defense and aerospace. It forced chemists, physicists, engineers to work together. It really cemented MS as a forward-looking, design-oriented discipline.
So bringing it to today, where does this knowledge become critical? I mean, beyond designing new gadgets.
Well, a huge area is forensic engineering. Failure analysis.
When things go wrong.
Exactly. When a bridge fails, or a plane part breaks, or an engine component gives out, Material scientists are essential. They have to meticulously analyze the failed part.
How do they do that?
They look at the processing history, the operating conditions, and crucially, the microstructure of the material near the failure point. Was it a manufacturing defect? Was it fatigue from repeated stress? Was it corrosion? Understanding the material's structure and properties is key to finding the root cause, preventing it from happening again.
That makes sense. And it brings us right back to that paradigm. Processing right arrow structure, right arrow performance. You keep emphasizing structure.
Because structure is king. The whole field is about understanding the relationships that exist between the structures and properties of materials. And we look at structure on different size scales. It's not just one thing.
Okay, break that down. What's the smallest scale?
We start at the atomic structure. We're talking angstroms here, 10 to the minus 10 meters. This is where it all begins. How individual atoms bond together, ionic, covalent, metallic bonds, and how they arrange themselves in space, which is crystallography.
So the type of bond and the arrangement, that sets the basic rules.
Pretty much. Things like electrical conductivity, magnetism, basic chemical reactivity, a lot of that is determined right here by the atoms and their immediate neighbors.
And in crystallography, you mentioned the unit cell.
Right. If you imagine building a crystal like stacking identical Lego bricks, the unit cell is the smallest repeating brick. It contains the fundamental pattern. Describe the unit cell, its size, shape, which atoms are where, and you've basically described the entire perfect crystal.
A perfect crystal, like you said earlier.
Exactly. Perfect crystals don't really exist outside of maybe a computer simulation. Real materials always have defects. Missing atoms, called vacancies, extra atoms squeezed in where they don't belong, called interstitials, misaligned planes of atoms, called dislocations.
And these aren't just annoying flaws.
Far from it. Often these defects control the most important properties. They're not bugs, they're features, you could say.
How so? Give me an example.
Okay, take metals. Why are they ductile? Why can you bend a paperclip instead of it just snapping?
Because it's metal.
Yes, but why? It's because of dislocations. Those line defects, those extra half planes of atoms. When you apply stress, these dislocations can move like a ripple through the crystal. That movement allows the planes of atoms to slide past each other without breaking the bonds completely. That's plastic deformation.
So the ability of metal to bend relies on these imperfections moving.
Precisely. If you had a theoretically perfect metal crystal with no dislocations, it would be incredibly strong, yes, but also incredibly brittle. It would shatter like glass. So material scientists spend a huge amount of time figuring out how to control the number and movement of dislocations to get the right balance of strength and ductility.
That's fascinating. The flaws are the key. And of course, not everything is crystalline, right? What about glass?
Good point. Some very important materials are amorphous. Glass is the classic example, many polymers too. They lack that long-range, repeating order of a crystal. The atoms are sort of jumbled together, more like a frozen liquid. That gives them very different properties.
Okay, so that's the atomic scale. What's the next level up?
We move up to the nanostructure. This is the scale from about 1 nanometer up to maybe 100 nanometers. This area has just exploded in the last couple of decades.
Why? What's special about that size range?
Because when you make structures this small, the physics starts to change. A huge fraction of the atoms are now on the surface or very close to it.
The surface area to volume ratio goes way up.
Exactly. And that means surface effects, quantum effects sometimes, start to dominate behavior. Materials at the nanoscale can have totally different electrical, optical, magnetic, even mechanical properties compared to the same material in bulk form.
So how do you categorize these nanostructures?
We often talk about their dimensionality. If only one dimension is at the nanoscale, like the thickness of a coating, you get things like nanotextured surfaces or thin films. If 2 dimensions are nanoscale, like the diameter of a wire or tube, you get nanowires or nanotubes, like the famous carbon nanotubes.
And 3 dimensions.
Then all 3 dimensions are confined to the nanoscale. That gives you nanoparticles, which can be roughly spherical, or quantum dots, tiny little chunks of material.
Okay, atomic, nano, what's next?
Next up is the microstructure. Now we're talking from roughly 100 nanometers up to maybe millimeters, but usually viewed under a microscope, say, above 25 times magnification. This is the traditional realm of metallurgy and ceramics engineering.
And what defines the microstructure?
This is where we see things like grains. Most metals and ceramics aren't single perfect crystals, they're polycrystalline. They're made up of many tiny individual crystals, called grains, all packed together.
Like a mosaic of tiny crystals.
Exactly. And each grain might have a slightly different orientation of its crystal lattice compared to its neighbors. The boundaries between these grains, the grain boundaries, are really important.
Why? What do the grains and boundaries affect?
Oh, tons of stuff. Strength, how easily a crack can travel through the material, toughness, ductility, even corrosion resistance. It's a huge factor.
Is there a simple rule like smaller grains are better?
Often, yeah. Smaller grains mean more grain boundaries. And grain boundaries act as obstacles to dislocation movement, those defects we talked about. So generally, a material with a finer grain structure is harder and stronger. There's actually an equation for it, the Hall-Petch relationship.
So engineers carefully control grain size during processing.
Absolutely. Using techniques like heat treatment or specific alloying additions. And they use tools like microscopy and powder diffraction to check that they got the microstructure they wanted.
Okay, that covers the micro level. Is there one more scale?
Yep. The last one is the macrostructure. This is what you can see with the naked eye. Millimeters, centimeters, meters. The overall shape of the part, any visible cracks, porosity from casting, stuff like that.
So less about fundamental properties, more about the finished object.
Generally, yes. While large flaws are obviously bad, the real control over the material's intrinsic properties happens down at the atomic, nano, and especially the microscales.
Okay, we've got structure covered across all scales. Now let's link it back to the other parts of the paradigm. How do we actually control that structure? That brings us to processing, thermodynamics, and kinetics.
Right. Processing is the how you make it part. It's absolutely critical. You can design the most amazing material on paper, but if you can't make it reliably and affordably, it's useless industrially.
So this includes things like casting metal, rolling steel, welding.
Yeah, all the manufacturing techniques. Sintering powders together to make ceramics, growing single crystals for semiconductors, laying down thin films for electronics. It's incredibly diverse.
And you mentioned control is key.
Mm-hmm.
How precise does it need to be? Like, does a tiny bit of something else really matter?
Oh, absolutely. Steel is the perfect example. Steel is basically iron plus carbon, but whether it's steel depends on the carbon being between about 0.01% and 2.00% by weight. That's a tiny range.
Within that range.
Tiny shifts make huge differences. Low carbon steel, maybe 0.1%, is soft and ductile, easy to shape. High carbon steel, maybe 1%, can be made incredibly hard. Good for tools, but it's more brittle. Controlling that carbon content and other trace elements down to fractions of a percent is everything in steelmaking.
Wow. Okay, so processing sets the structure.
Yeah.
But how do we know what structures are even possible or how they'll change? That's where the other two come in.
Exactly. We need the laws of thermodynamics and the rates of kinetics.
Thermodynamics first. That's about energy and stability.
Right. Thermodynamics tells you what's possible from an energy perspective. Will this reaction happen? Will this phase transform into that phase at this temperature? It defines the stable states using concepts like energy and entropy. If a change requires too much energy input or leads to a much less stable state, thermodynamics says, nope, not going to happen spontaneously.
So it sets the boundaries, the rules of the game.
You got it. And the most practical tool that comes directly out of thermodynamics for materials scientists is the phase diagram.
I've seen those. They look like complex maps.
They are, but they map out which phases, solid, liquid, different crystal structures, are stable at different temperatures and compositions for a given material system, like iron and carbon for steel. They are indispensable for designing heat treatments and understanding alloys.
Okay, so thermo says if a change can happen, but not how fast.
Exactly. That's the job of kinetics. Kinetics is all about the rate of change. How quickly does that transformation actually occur? How fast do atoms move around?
Like your mountain climber analogy, thermo says you can reach the summit. Kinetics tells you if you'll get there before dark.
Perfect analogy. In materials, the most important kinetic process is usually diffusion, the movement of atoms within the material.
How does that work in a solid? Atoms are locked in place, aren't they?
Mostly, but remember those vacancies, those empty spots. An atom can jump into an adjacent vacancy, leaving its old spot empty. It's like a slow-motion atomic square dance.
Vacancy diffusion.
That's the main way atoms move around in solids. And it takes time, and it's highly dependent on temperature. Heat things up, atoms vibrate more. Diffusion happens much faster.
And this is crucial for processing.
Absolutely critical. When you heat treat steel, for example, you're relying on kinetics. You hold it at a certain temperature for a specific time to allow carbon atoms to diffuse where you want them, to allow the microstructure to rearrange into the desired state. Too short or too cold, and the change doesn't happen properly. Kinetics dictates the time element of processing.
Processing, guided by thermo and kinetics, creates the structure, which gives the properties and performance. It all fits. Okay, let's talk about the actual materials we use. What are the major categories?
Originally, we grouped them into three main families: ceramics and glasses, metals and alloys, and polymers. And then there's a fourth important category that overlaps: composites.
Can we make this relatable? We used a great analogy before the beverage container.
Right. It shows the trade-offs perfectly. Think about a glass bottle. Glass is a ceramic. Pros: it's transparent, cheap raw materials, keeps the fizz in, good gas barrier, recyclable. Cons: heavy, and it shatters easily. It's brittle.
Okay, then an aluminum can, metal alloy.
Pros: pretty strong for its weight, excellent barrier, recyclable. Cons: opaque, making it uses a lot of energy, it dents easily.
And finally, a plastic bottle.
Polymer. Pros: super lightweight, cheap to mass produce, doesn't shatter like glass. Cons: not as good a gas barrier. Your soda goes flat faster. So you see, no single material is perfect for everything. It's always about choosing the best set of properties for the job.
Makes sense. Let's dive into ceramics and glasses then. What defines them?
These are typically inorganic, non-metallic compounds, often oxides, nitrides, carbides. Think pottery, cement, glass, bricks. Their calling cards are usually hardness, stiffness, high temperature stability, good insulation, electrical and thermal, and often good wear resistance.
But the big drawback is brittleness, right? They tend to fracture.
That's historically been the main limitation, yes. They don't have those easily moving dislocations like metal, so when a crack starts, it tends to just zip right through.
But scientists have found ways around that. You mentioned crack deflection.
Yeah, this is a clever microstructural engineering trick. You embed strong secondary particles or fibers within the ceramic matrix. When a crack tries to run, it hits these obstacles and has to go around them.
Changing direction takes energy.
Exactly. It forces the crack down a longer, more difficult path, which absorbs energy and makes the whole material much tougher, less prone to sudden failure. It's a key principle in advanced ceramics, even in things like tough smartphone screens.
Like Corning's Gorilla Glass.
That's a great example of engineering the structure and composition to dramatically improve fracture resistance in a traditionally brittle material.
Okay, moving on to metal alloys.
Yeah.
You said iron alloys dominate.
By sheer tonnage, absolutely. Steel, stainless steel, cast iron, they're the workhorses of construction, automotive infrastructure.
And we already touched on steel iron plus carbon, controlled by heat treatment. Can you elaborate on that heat treatment process? Quenching and tempering?
Sure. So you heat the steel up high enough to dissolve the carbon within the iron's crystal structure. Then you quench it, cool it down really fast, usually in water or oil.
What does the rapid cooling do?
It traps the carbon atoms where they are, preventing them from diffusing out and forming softer phases. Instead, it forces the iron lattice to distort into a very strained, hard structure called martensite. It's extremely hard, but also very brittle.
Too brittle to be useful, usually.
Often, yes. So that's where tempering comes in. You gently reheat the quenched steel to a lower temperature, maybe a few hundred degrees C. You hold it there for a while.
Letting the atoms move a bit. Kinetics again?
Precisely. It allows just enough diffusion for some of the carbon to precipitate out as tiny carbide particles, and it relieves some of the internal stress in the martensite. The result is a material that's still very strong, but significantly tougher and more ductile. You trade a little hardness for a lot more toughness. It's a classic materials engineering balancing act.
Beyond steel, what other metals are important?
Well, for high-performance applications, especially where weight is critical, we look at alloys of aluminum, titanium, and magnesium. Think aerospace, high-end cars, performance bicycles.
Why those?
They offer fantastic strength-to-weight ratios. Titanium, for instance, can be as strong as steel, but is about 40% lighter. It's also incredibly corrosion-resistant, which is why it's used in jet engines and medical implants.
But they're more expensive.
Generally, yes. Extracting and processing them is more complex and energy-intensive than steel. Aluminum needs electrolysis. Titanium is tricky because it reacts easily. So you use them where the performance benefits justify the cost.
Okay, third family, polymers, plastics and rubbers. What's their deal?
Polymers are all about long chains. They're made of repeating molecular units called monomers, linked together into massive molecules, sometimes millions of atoms long.
And that chain structure gives them unique properties.
Definitely. The things like flexibility, low density, ease of molding into complex shapes. Their properties depend hugely on the type of monomer, how long the chains are, and how the chains interact with each other. Are they tangled like spaghetti, or can they line up more neatly?
You also mentioned versatility comes from additives.
Oh yeah, hugely. Take PVC, polyvinyl chloride. Pure PVC is rigid, used for pipes, but add plasticizers, small molecules that wedge between the polymer chains and let them slide past each other more easily, and it becomes flexible, suitable for things like vinyl flooring, wire insulation, or even shower curtains. Additives can change color, UV resistance, flame retardancy. It's like a molecular toolkit.
How are polymers classified?
Often by their application and performance. You have commodity plastics like polyethylene, PE, for plastic bags, polypropylene, PP, for containers, cheap, high-volume, disposable stuff.
Yeah.
Specialty plastics designed for specific unique properties, maybe high temperature resistance or unusual optical behavior, and then engineering plastics.
These are the high-performance ones.
Right. They offer superior mechanical properties, strength, stiffness, wear resistance, stability at higher temperatures. Things like polycarbonate, nylon, and a really interesting one, ultra-high molecular weight polyethylene, UHMWPE.
What's special about that one?
The polyethylene chains are just incredibly long, millions of repeating units. This creates a material that is remarkably tough, abrasion-resistant, and has an extremely low coefficient of friction.
So useful for things that need to slide or resist wear.
Exactly. It's used in industrial wear strips, conveyor belt parts, and famously as the socket liner in artificial hip and knee joints because it slides so well against the metal or ceramic ball.
Amazing. Okay, the final category, composites. What makes them different?
Composites are mixtures, but on a macroscopic scale. You take two or more distinct materials, often a reinforcing material, like fibers, embedded in a matrix material, like a polymer resin, and combine them to get properties better than either component alone.
So not like an alloy where elements are mixed at the atomic level.
No, you can typically see the different phases in a composite, at least under a microscope.
Yeah.
Think of fiberglass fibers in a polymer matrix, or carbon fiber reinforced plastics used in aircraft and sports equipment.
You had a really dramatic example, the space shuttle material.
Ah, yes. Reinforced carbon-carbon, RCC. That stuff is incredible. It was used on the wing leading edges and nose cap, the parts that got hottest during re-entry.
How hot are we talking?
Upwards of 1,500 degrees Celsius. Just white hot. RCC could handle it.
How is it made? What's its structure?
It's a multi-step process, really clever engineering. You start with layers of graphite cloth made from rayon fibers. You impregnate this with a phenolic resin, cure it, then bake it at high temperature in an inert atmosphere. This pyrolyzes the resin, turning it into pure carbon, binding the cloth layers together.
So now it's basically carbon fibers held together by a carbon matrix, carbon-carbon.
Exactly. But pure carbon, while strong at high temps, burns easily in oxygen. So the final, crucial step was applying a coating of silicon carbide.
Why silicon carbide?
It forms a protective layer that resists oxidation at those extreme temperatures. So the silicon carbide protected the structural carbon for strength, the silicon carbide for protection to achieve performance neither could manage alone. A true composite solution.
That's incredible engineering. Okay, let's shift gears now to the cutting edge. Where is material science research focused today and tomorrow?
Well, we have to start with semiconductors. They're not new exactly, but the advances are constant, and they are the absolute bedrock of modern electronics. The whole digital world runs on them.
It's a massive industry.
Huge. Over $500 billion globally. And it all relies on materials whose electrical conductivity is somewhere between a conductor like copper and an insulator like glass.
And the key is controlling that conductivity.
Precisely. Using a process called doping. You start with an ultra-pure semiconductor crystal, usually silicon, and intentionally introduce tiny, tiny amounts of impurity atoms.
Impurities.
Yeah.
Like flaws again.
Sort of, but these are deliberately added. If you add an element with one more valence electron than silicon, like phosphorus, you get extra electrons that can carry current. That's N-type silicon. If you add an element with one fewer valence electron, like boron, you create holes where electrons are missing. And these holes can act like positive charge carriers. That's P-type silicon.
And putting N-type and P-type together
Yeah.
lets you build devices.
Exactly. The junction between N and P-type regions is the heart of diodes and transistors, the fundamental building blocks of integrated circuits. The ability to precisely control doping is everything.
Silicon is the king, you said.
By far. It's abundant, cheap, and its natural oxide, silicon dioxide, is an excellent insulator, which is incredibly convenient for making transistors, but it's not the fastest.
What's faster?
For really high-speed applications, like in your mobile phone's signal processing or in radar systems, gallium arsenide, GAs, is often preferred. Electrons simply move through GAs much faster than silicon.
Higher electron mobility.
Right. The downside is that GAs is more expensive and harder to process than silicon. So again, it's a trade-off cost versus performance.
Okay. Beyond semiconductors, what's hot? We talked about the nanostructure scale earlier.
Yes, and nanomaterials research as a dedicated field is booming, really focusing on exploiting those unique properties that emerge between 1 and 100 nanometers.
Like carbon nanotubes.
Carbon nanotubes are a prime example, along with graphene, which we'll get to, fullerenes, buckyballs, and various nanoparticles. Their potential is enormous: stronger composites, better catalysts, new types of sensors, more efficient energy storage. The list goes on.
Another really important frontier seems to be where materials meet biology.
Absolutely. Biomaterials science. This is all about designing materials that can interact safely and effectively with biological systems with the human body, usually.
So things like implants?
Implants are a huge part of it. Artificial joints, heart valves, dental implants, stents, but also materials for drug delivery systems, where a material might slowly release medication inside the body, or materials for tissue engineering scaffolds designed to help the body regenerate damaged tissues.
Does the body react to these materials?
That's the key challenge. You need biocompatibility. The material shouldn't cause harmful inflammation or rejection. Sometimes you want the material to be inert, just tolerated by the body. Other times you want it to be bioactive.
Bioactive, meaning it interacts chemically.
Yes. For example, coating a titanium hip implant with hydroxylapatite, a calcium phosphate ceramic similar to bone mineral. This encourages the patient's own bone cells to grow onto and bond directly with the implant surface, creating a much stronger, more stable integration. It's really sophisticated stuff.
And driving a lot of this progress is computing power, right?
Definitely. Computational materials science is transforming the field. We can now simulate how atoms and molecules interact, predict crystal structures, model defect behavior, calculate properties.
Yeah.
All before we even make the material in the lab.
Using techniques like molecular dynamics.
Molecular dynamics, density functional theory, powerful simulation tools. The big dream here is something called integrated computational materials engineering, or ICME.
What's the goal of ICME?
To link simulations across all the scales from atoms up to the final component with real-world experiments. The idea is to dramatically speed up the design process. Instead of years of trial and error lab work to develop a new alloy, maybe you can do most of the optimization on a computer in weeks.
Digital prototyping for materials.
That's a good way to put it. It promises to make the discovery and deployment of new materials much, much faster.
Okay, so with all this research power, what are some of the really exciting emerging technologies we should watch out for? Where does it get really interesting?
Well, the sources point to a few game changers. First, graphene. We mentioned it briefly. A single layer of carbon atoms arranged in a honeycomb lattice.
The thinnest material possible.
Pretty much. And it's incredibly strong, way stronger than steel, very light, and an amazing conductor of electricity and heat. The potential applications are just staggering.
Like what?
Faster transistors, maybe replacing silicon in some areas, flexible, transparent conductive films for touchscreens or solar cells, membranes for water filtration, high-capacity energy storage, efficient hydrogen storage for fuel cells. It's still early days for large-scale production, but the promise is immense.
Okay, what else?
Metamaterials. This is mind-bending stuff. These aren't materials defined by their chemistry, but by their engineered structure, usually on the micro or nanoscale. They're designed to interact with light or other electromagnetic waves in ways no natural material can.
Like the invisibility cloak idea.
That's the most famous potential application. Yes, materials that could bend light around an object, but also potentially revolutionary lenses, antennas, or materials that absorb sound or vibrations in unique ways. It's really about controlling wave propagation through structure.
Very futuristic. Anything else?
Quantum dots. These are those tiny semiconductor nanocrystals we mentioned earlier, just a few nanometers across.
And their properties depend on their exact size.
Exactly. Because they're so small, quantum mechanics dictates their behavior. Specifically, the color of light they emit when excited depends directly on their diameter. Smaller dots emit bluer light, larger dots emit redder light.
Where could that be used?
The most immediate application is in displays. Quantum dot TVs are already on the market, offering brighter colors and better energy efficiency than traditional LCDs. They're also being explored for high-speed optical communications, biological imaging, even quantum computing.
It sounds like the control over structure is reaching an incredible level of finesse.
It really is. And that brings us back full circle. The power of material science lies in that unified approach. Understanding structure across all those scales, atomic, nano, micro, and learning how to control it through processing, using the rules of thermodynamics and the timing of kinetics, all to achieve the specific properties needed for the desired performance.
So for you listening, the big takeaway here is just how fundamental this field is. If you're interested in any kind of engineering or technology, understanding materials is just essential. It connects physics, chemistry, mechanical engineering, electrical engineering. So it's a common language.
Every new material opens up entirely new possibilities. Think about how silicon changed the world, or how plastics revolutionized manufacturing. The materials we discover and engineer define what's possible technologically.
We've covered a lot: steel, silicon, polymers, composites, these amazing new frontiers. But let me leave you with a final thought, something to chew on. The sources make it clear this field is constantly evolving, driven by computation, by biology, by new physics.
There's always something new around the corner.
So think about the material we didn't name today, the one that's maybe just an idea in a simulation right now, or a curiosity in a biomaterials lab. What material, perhaps emerging from quantum science or AI-driven design, will be the next silicon? The one that defines the next great technological leap for humanity? That's the question material science is working on right now.
A fascinating question indeed. Thanks for joining us for this deep dive.
We'll see you next time on The Deep Dive.
Welcome back to The Deep Dive. If you're looking for a crash course in how fast the mighty can fall, well, you've definitely come to the right place today. We are immersing ourselves in AD 69 Tennessee. It's known simply as the Year of the Four Emperors. And honestly, it might be the single most chaotic, bloody, and politically consequential year in all of Roman history.
It really is something else. This isn't just, a minor blip. This is the moment the Roman Empire fundamentally broke from its founding principles. For almost a century, power had flowed, maybe imperfectly, but flowed nonetheless, through the Julio-Claudian bloodline, Augustus's legacy.
Right. And in AD 69, that foundation just imploded completely. It led to this rapid, incredibly violent succession. First Galba, then Otho, then Vitellius, and finally the one who stuck, Vespasian. He's the one who founded the Flavian dynasty, which brought back some stability. And the sources we're diving into today, they really confirm this wasn't just some power struggle happening quietly in the Senate buildings in Rome.
No, not at all.
This was the empire's first real full-blown civil war. It's a terrifying look at how raw military power, wielded by legions stationed way out in the provinces, far from the capital, could suddenly dictate the fate of the entire known world.
So our mission for you today really is to trace that brutal succession. We're tracking events that incredibly spanned less than 18 months in total, from start to finish.
It's staggering.
It is, and we want to try and pinpoint the critical miscalculation, you could call it the fatal flaw, of each of those first three rulers, Galba, Otho, Vitellius, and show how this expectation of massive transactional military loyalty, basically measured in mountains of cash, became the only real measure of legitimacy.
Was less than 18 months for that much upheaval. The entire sequence starts with the revolt that forces Nero's suicide in June of 68, and it ends with Vespasian finally being recognized in December 69. It just shows a complete meltdown of central authority.
And the core insight, right from the get-go, the thing we really need to keep coming back to, is that the decisions about who gets to be emperor, they weren't being made by the senators in their togas in Rome anymore. Not really. They're being made by battle-hardened soldiers, often on distant frontiers. It just confirms that the legions had become the ultimate kingmakers. And that structural shift, it fundamentally changed how the empire worked for the next couple of centuries.
Okay, so let's dive into part one. We need to start with that first domino, the end of the Julia Claudians, Nero's fall, and then the very brief and frankly disastrous reign of Servius Sulpicius Galba.
Right, the collapse really starts, as these things often do, with plots simmering against the current ruler, Nero.
He wasn't exactly popular by the end, was he?
No, the political atmosphere was toxic. You'd already had the Pesonian conspiracy back in AD 65, which involved some pretty prominent senators, military figures. The elite were just deeply, deeply unhappy with Nero's perceived tyranny, his spending.
His whole vibe, really.
Exactly. But they didn't really have a candidate strong enough or maybe brave enough to step up and replace him.
So the spark comes from outside Rome? From the province?
Precisely. Mid-March AD 68, a guy named Gaius Julius Vindex, he's the legate, the governor of Gallia Lugdunensis, that's central Gaul. He launches this massive revolt. And what's really interesting, maybe even strategically brilliant about Vindex, is what he didn't do. The sources are quite clear.
Yeah.
He didn't declare himself emperor.
Ah, smart.
So he's not trying to grab power for himself. He's just anti-Nero.
Exactly. That non-candidacy was key. It maximized his chances of finding allies. By just declaring himself an enemy of Nero, he could basically shop around for someone with the right connections, Senate ties, military background.
And he finds Galba.
He settles on Servius Sulpicius Galba. He is the governor of Hispania Tarraconensis, so Spain. Elderly guy, very respected family background, but known for being, well, notoriously strict. Rigid.
Okay.
Galba accepts the offer, and his own legion in Spain acclaims him emperor in Carthago Nova. That's early April 68. But this initial move almost collapses straight away, right? Vindex doesn't last long.
No. This early alliance gets crushed pretty quickly. It shows the power disparity between different provincial armies. Vindex's forces, they were mostly Gallic auxiliaries, local levies, not exactly top-tier Roman legionaries.
And they run into
the professional, battle-hardened Rhine legions. These guys were commanded by Lucius Virginius Rufus. The clash happens at the Battle of Assaltia.
And the Rhine legions win easily.
Decisively. You know, these Rhine legions, they were veterans of constant fighting against Germanic tribes. Tacitus really highlights the ethnic tension here, too. The Roman veterans apparently had intense contempt for the Gallic auxiliaries fighting with Vindex. They saw them as unreliable.
So Vindex loses.
He commits suicide right after the defeat. But what makes this critical is what happens next. The Rhine legions, even though they crushed Vindex, they really disliked Galba. They remembered him from a previous harsh governorship.
Okay.
So they try to acclaim their own commander, Virginius Rufus, as emperor. But he refuses. He turns it down flat.
Wow, why?
It's debated. Maybe loyalty to the Senate, maybe pragmatism. But the result, the most powerful military machine in the empire, the Rhine army, is suddenly left without an emperor to follow. A dangerous military vacuum is created right there in Central Europe.
Okay, so the action then shifts back to Rome, inside the Praetorian Guard.
Yes, the crucial betrayal happens there. A man named Nymphidius Sabinus, he was the deputy prefect of the Praetorian Guard. He sees his chance.
What does he do?
He convinces the Praetorians, the emperor's personal bodyguards, to abandon Nero. And he does it with this radical, absolutely game-changing offer, supposedly in Galba's name.
Money.
A staggering amount of money. 30,000 sesterces for every single guardsman.
30,000. How much is that in real terms? Okay, put it this way. That's roughly 10 years of a standard legionary's base pay, paid out as a massive one-time cash bonus.
Wow. Okay.
This moment, you could argue, it redefined imperial transitions forever. It set this deadly precedent that loyalty wasn't about duty or tradition anymore. It was purely transactional. And the price was now exorbitantly high. That's the structural shift right there, isn't it? The emperor is no longer just a ruler. He's the highest bidder.
Pretty much. And it works. The Praetorians desert Nero. On June 9th, 68, the Senate, seeing which way the wind is blowing, declares Nero a public enemy. Nero flees Rome and commits suicide. And Galba is formally recognized as the new emperor.
So Galba gets the throne, but his reign, it lasts barely 7 months, just about 7 months, and it fails mainly because of this toxic mix. On one hand, extreme fiscal austerity, it was famously tight-fisted, and on the other, just overt cruelty.
Yeah, the sources really don't pull any punches about his arrival in Rome.
Yeah.
Tacitus calls his journey a long and bloody march. It doesn't sound like a victory parade.
No, it was basically a path paved with executions. He targeted officials he thought were corrupt or disloyal from Nero's time, like Bituus Silo and Obultronius Sabinus, executed on the way. But maybe the most shocking display of this kind of lethal rigidity happened just before he even entered the city of Rome itself.
What was that? Well, Nero, in his desperate final days, had formed a brand new legion, Legion Weighty Adjutrix. He recruited it from Roman sailors serving in the fleet at Misenum, and he promised them full legionary status and pay.
Okay, a big step up for sailors.
A huge step up. So when Galba is approaching Rome, these sailors march out unarmed to meet him and press their case. They want him to confirm their new, expensive legionary status.
And Galba's reaction.
Terrifying. Instead of negotiating, or even just delaying, he orders his own veteran troops to charge them. Right there, near the Milvian Bridge.
He attacked unarmed Roman sailors.
Yes. Thousands were killed in the initial charge. It was a massacre. And then, to add insult to horrific injury, he subjected the survivors to a decimation.
A decimation? What does that even mean?
It's an old, incredibly brutal form of military punishment. It hadn't really been used reliably since the time of maybe Tiberius. Basically, the surviving soldiers are divided into groups of 10. They draw lots, and one man in each group is chosen to be executed by his own 9 comrades.
Executed by his own unit.
Yes. It was designed to crush morale completely, instill absolute terror. This act, right on the doorstep of Rome, just solidified this image of Galba as harsh, unfeeling, frankly tyrannical.
It's hard to recover from that image.
Absolutely. And we should add a little caveat here.
Right.
Our main source for a lot of this detail is Tacitus. And Tacitus was writing later under the Flavian dynasty, Vespasian's family.
Ah, so the guys who replaced Galba, Otho, and Vitellius.
Exactly. So the Flavians had every reason to paint Galba, Otho, and Vitellius as villains, whose failures justified Vespasian having to step in and clean up the mess. But even allowing for that potential bias, Galba's actions seemed disastrously counterproductive.
And then came the really critical mistake, the financial one.
Yes. He absolutely refused to pay the Praetorian Guard that massive 30,000 sesterces bribe that Nymphidius Sabinus had promised them in his name.
The bribe that got him the throne in the first place.
The very one. The Praetorians, who had risked everything by deserting Nero, were now furious. They felt fundamentally cheated. And the guy who'd actually engineered the bribe, Nymphidius, he was already dead. He tried to make a bid for emperor himself shortly after Nero's death, and the guards killed him for his trouble.
So the guards got rid of Nero, got rid of the fixer, but still didn't have their money.
Precisely. The resentment was immediate. It was palpable. And Galba just made things worse. He surrounded himself with these 3 apparently greedy advisors from his time in Spain, and he made some terrible appointments out in the provinces. Maybe none worse than sending Aulus Vitellius.
Vitellius, the next emperor in line.
The very same. Whom our sources basically describe as a penniless glutton, completely lacking in ambition or competence, sending him to govern the crucial province of Germania Inferior, commanding those powerful Rhine legions.
Why would he do that?
The thinking, perhaps, was that Vitellius was seen as weak, pliable, someone who wouldn't cause trouble. Big mistake. By January 1st, 69, those Rhine legions, still angry about how Vindex's revolt was handled, still disliking Galba, they refused to swear the annual oath of allegiance to Galba.
A direct challenge.
A massive challenge.
Yeah.
And the very next day, January 2nd, they acclaimed their governor, Vitellius, as the new emperor. This forced Galba's hand back in Rome.
He needed to show strength, stability.
Yes. Galba was old. He was childless. He desperately needed an heir to stabilize this situation, to show there was a future for his reign. And this leads to his final, terminal mistake, which was really down to, you could say, political snobbery.
What did he do?
He chose a young, very austere, respected senator named Lucius Calpurnius Piso Licinianus as his adopted son and heir.
Okay, and the problem was?
The problem was who he didn't choose. He publicly snubbed Marcus Salvius Otho.
Otho,
Yeah.
emperor number 2.
Number 2. Otho had been one of Galba's earliest and most prominent supporters. He'd governed Lusitania, modern Portugal, well. He was ambitious, popular in some circles, and crucially had widely publicly expected to be adopted by Galba. The snub was huge.
And Otho knew the Praetorians were unhappy.
He knew intimately how angry the Praetorian Guard were about the unpaid bribe.
Right.
So Otho basically used his own considerable personal wealth to finish the job Galba refused to pay for. He offered the guards a fresh, massive bribe.
So he buys the guards' loyalty away from Galba?
Essentially, yes. And it happens incredibly fast. Just 2 weeks after Piso's adoption, on January 15th, 69, Galba and his newly adopted heir Piso were ambushed right in the Roman Forum by the Praetorians.
And murdered.
Murdered on the spot. The image the sources give us is horrifying and iconic. Their heads were cut off, impaled on poles, and paraded through the city streets.
A brutal message. It confirmed absolutely to everyone, senator, soldier, ordinary citizen, that the traditional power of the Senate was basically obsolete. The legions, or in this case the Praetorians in Rome, were now in charge of regime change. And the price of loyalty had been set, 30,000 sesterces, minimum. So the military, specifically the Praetorians, have now crowned Otho, effective immediately, January 15th, 69. We go straight from Galba's fatal stinginess to Otho's brief, maybe more populist rule.
Right. The Senate, probably terrified and just desperate for some kind of stability, recognized Otho immediately. And initially, Otho was actually seen as a bit of a relief compared to Galba.
How so?
Well, he'd been close to Nero in his youth, which wasn't necessarily a good thing, but his personal history suggested he was cunning, ambitious, but maybe not deeply cruel like Galba seemed. He gained popularity pretty quickly by handing out favors, restoring statues of Nero, and consciously trying to emulate Nero's successful early years, promising stability, popular entertainment. He was expected to be reasonably fair, especially to the soldiers who just put him on the throne.
Okay, so he starts off okay. But if Galba failed because of internal issues, cruelty, money, Otho faces the opposite problem almost instantly, right? His success in Rome makes him a target for someone with much stronger forces outside Italy.
Exactly. The threat is Vitellius. He's been acclaimed emperor by those crack Rhine legions just days before Otho took power in Rome.
And these Rhine legions are serious business.
Arguably the best soldiers in the world at that time. We're talking veterans from legions like I Germanica, XXI Rapax. These guys were hardened by constant warfare on the German frontier, highly professional, perfectly positioned in Central Europe to march south. Otho's forces, meanwhile, they were mixed, some Praetorians, some city troops, the newly formed Sailor Legion, Iadiutrix, maybe some legions summoned from elsewhere, but generally not considered as tough as the Rhine army.
Did Otho realize how serious the threat was?
Oh, absolutely, straight away.
Yeah.
And we see this remarkable detail in the sources. He actually tried really hard to avoid a civil war. He sent messengers to Vitellius proposing peace, offering to share power, even offering to marry Vitellius's daughter, trying to negotiate his way out.
Shows a certain political pragmatism, doesn't it? But it was far too late. Vitellius's top generals, Aulus Caecina Aelianus and Fabius Valens, were already on the move. They were leading about half of Vitellius's superior army south, marching over the Alps, heading straight for Italy.
And this leads to the first big battle of the Civil War proper.
Yes, the first Battle of Dedriacum. It's fought near Cremona in northern Italy. It's not always a battle that gets a lot of attention in popular histories, but it was absolutely decisive for this phase of the war.
What happened there?
Well, it was more of a campaign with several skirmishes, but the main showdown came on April 14th, 69. Otho's forces were pretty badly beaten. It really came down to the superior quality, the discipline, maybe the leadership of the Rhine legions under Caecina and Valens. So Otho loses his first major test.
Yeah, he does. And now Otho, who's only been emperor for about 3 months, faces this stark choice. He still had reserve troops. He could try to rally, maybe attempt a counterattack, prolong the bloodshed, or he could surrender and accept defeat.
And his decision is kind of the historical irony of his short career, isn't it? The guy who bribed and murdered his way to power.
Ends his reign with what many historians, even ancient ones like Tacitus, portray as a profoundly noble act, an act of self-sacrifice.
Commit suicide.
He commits suicide the very next day, April 16th. And the sources, particularly Tacitus and Plutarch, suggest he did this very deliberately, stating he wanted to end the anarchy, to prevent the empire from tearing itself apart in a prolonged civil war over him.
That's unexpected. It is.
Yeah.
It raises this critical question, though. Was his sacrifice immediately forgotten or ultimately futile? Because the legions who had fought for him, they mostly just surrendered to Vitellius's generals anyway. Otho showed a kind of conscience, maybe, that none of the other contenders really possessed, yet his nobility didn't secure any lasting loyalty or legacy for his cause. He was just gone. So Act 2 ends, and Vitellius takes the stage. He's recognized by the Senate on April 19th. Now, if Galba was the rigid miser and Otho was the ambitious pragmatist who maybe found a conscience at the end, what defines Vitellius?
Well, if you believe Suetonius especially, Vitellius was defined by a specific kind of soft corruption, maybe, just staggering, ruinous decadence.
Yeah.
Gluttony, essentially.
Right from the start, pretty much. His reign seems marked by bad omens and poor judgment almost immediately. For instance, a really superstitious mistake he made. He chose the anniversary of the Battle of the Alarale. What's that?
It was a catastrophic Roman military defeat against the Gauls way back in 390 BC. A day considered deeply unlucky, a day of bad auspices in Roman superstition. Vitellius chose that specific day to formally accept the office of Pontifex Maximus, the chief priest.
That sounds deliberately provocative or just clueless.
Either way, it was seen as a massive affront to Roman tradition. It deeply unsettled the traditional elite in Rome.
Okay, so bad omens. But that's not a financial crisis in itself. You mentioned gluttony. Suetonius goes into detail.
Oh, Suetonius is almost obsessed with it.
Yeah.
And we're not talking about someone who just enjoyed a good meal.
Mm.
We're talking about an emperor who reportedly held 3, sometimes 4, enormous, lavish banquets every single day, morning, afternoon, and night.
3 banquets a day. How is that even possible? Suetonius gives these incredible details, banquets costing maybe 400,000 sesterces each. He mentions one specific famous dish allegedly created for Vitellius. This colossal silver platter, nicknamed the Shield of Minerva, filled with an insane mix of rare delicacies, pike livers, pheasant brains, peacock brains, lamprey roe, things brought by the fleet from Parthia to Spain. That sounds obscene.
And expensive.
Wildly expensive. To support this lifestyle, not just for himself, but for the massive entourage of German veterans who'd marched with him to Rome and expected to share in the spoils, Vitellius basically drove the imperial treasury towards bankruptcy almost instantly.
Okay, so this seems like his critical miscalculation. He's alienating the wealthy elites, the people whose money he actually needs to run the empire, let alone pay his troops consistently.
Exactly. And when the moneylenders, the financiers in Rome, understandably started asking for repayment of the vast slaves being borrowed or spent, well, that's when Vitellius's truly nasty side emerged. What did he do?
His response, according to the sources, was pure tyranny. He allegedly resorted to torture and execution against creditors who dared to demand their money back.
Seriously, and even worse, Suetonius claims he developed this systematic practice. If a wealthy citizen named Vitellius as one of their heirs in their will, maybe hoping for favor, Vitellius would sometimes have them killed, often along with any co-heirs, just so he could seize the entire inheritance immediately, before they had a chance to change the will. He's ruling like a bandit chief, not an emperor.
Pretty much. It meant his actual support base became incredibly narrow. It really didn't extend much beyond those German veterans who were gorging themselves at his banquets in Rome. This left him completely vulnerable when the next challenge inevitably arose.
And while Vitellius is busy with, pheasant brains and assassinating creditors, the final and ultimately successful claimant is maneuvering into position. Titus Flavius Vespasianus. Vespasian, that's him. And Vespasian had this huge strategic advantage. He wasn't caught up in the chaos in Rome or Italy at all. He was far away, serving as the legate, the commander, in Syria. More specifically, he was commanding the massive Roman army fighting the major First Jewish-Roman War down in Judea. So he's a serious military commander out in the east.
A very successful, very pragmatic military man, known for being competent, relatively frugal, sober, basically the complete opposite of the mess Vitellius was making back in Rome.
And how does his bid for power start?
His acclamation as emperor was actually a moment of, well, political genius. It happened first not in Judea but in Alexandria, Egypt, on July 1st, 69. The prefect of Egypt, Tiberius Julius Alexander, declared for him.
Alexandria, why Egypt?
Because Egypt was the breadbasket of Rome. By securing control of Egypt, Vespasian immediately controlled the vital grain shipments that fed the city of Rome.
Ah, that's huge leverage. Starve the capital into submission.
It gave him immense leverage, both military resources from the province and huge psychological power over the capital. And from there, support snowballed. He quickly gained the backing of his own legions in Judea and Syria, and crucially, he won the allegiance of the powerful Danubian legions.
The Danube legions, weren't they the ones who fought for Otho earlier?
Many of them had, yes. They'd been defeated by Vitellius's forces at First Bedriacum. Now they were resentful, looking for a new, credible leader to back against Vitellius. Vespasian fit the bill perfectly. He also picked up support from former Galba supporters, anyone really who wanted Vitellius gone.
So Vespasian builds this broad coalition. Does he immediately march on Rome himself?
No. And this shows his strategic thinking, his patience. He actually traveled to Alexandria himself. He stayed there for a while to personally oversee and secure that all-important grain supply. Logistics first. He delegated the actual military advance on Italy to his trusted friend and ally, Gaius Licinius Mucianus.
Mucianus. Who was he?
He was the governor of Syria, another very capable political and military operator. Mucianus began marching west towards Italy with a strong force drawn from the Syrian and Judean legions. Meanwhile, Vespasian's son, Titus, the future emperor Titus, stayed behind in Judea to continue prosecuting the war there.
So the plan is for Mucianus to lead the invasion.
That seems to have been the plan. But things happened faster. Those Danubian legions we mentioned. They were eager for revenge against Vitellius's forces. They were led by a very aggressive commander named Marcus Antonius Primus, and they were impatient. They didn't wait for Mucianus and the main Eastern army to arrive.
They just went for it.
They invaded Italy on their own initiative, probably around August or September of 69, much faster than anyone expected.
And this rapid invasion forces the second major military clash of the year.
Exactly. The Second Battle of Bedriacum. Fought again near Cremona, same area as the first battle, but this time with different armies facing off.
And the outcome?
In October 69, Primus's Danubian army met Vitellius's forces. Vitellius's army was by now quite demoralized, maybe poorly led, certainly scattered. The Danubian legions, unified, highly motivated, fighting for a commander Vespasian who promised stability and competence. They won a crushing victory.
So Vitellius's main army is shattered. He's trapped in Rome.
Essentially, yes. He became increasingly desperate. He tried frantically to win over the people in the city with massive bribes, but the treasury was empty thanks to his earlier extravagance. He tried to levy troops from allied tribes, like the Batavians up near the Rhine, but they largely refused to get involved or were already leaning towards Vespasian.
Any other attempts?
Well, in a particularly pathetic move, as Primus's army neared Rome, Vitellius sent out emissaries to negotiate a truce. And incredibly, he had them accompanied by the Vestal Virgins, hoping their sacred status would force the invaders to stop.
Did it work?
No. The truce failed instantly. Primus wasn't going to be stopped by ceremony. Vitellius, now surrounded, seems to have panicked. He tried to flee the city, apparently went into hiding for a bit, but then made the fatal mistake of returning to the imperial palace one last time.
And Vespasian's forces caught him there.
Yes. On December 20th, 69, Vespasian's soldiers, who were now entering the city, found him hiding in the palace.
And his end, was it quick?
No. According to Suetonius, it was particularly ignominious. He was dragged out, apparently half-dressed, abused, pelted with filth by the crowds, forced through the city streets with a sword pointed under his chin to keep his head up, all the way to the Gemonian Stairs.
The Gemonian Stairs, where they threw criminals' bodies into the Tiber.
That's the place. He was brutally killed there, his body thrown into the river. A truly grim end, marking the definitive conclusion to the four-man race for power within Rome itself.
And the Senate.
The Senate, ever pragmatic, quickly acknowledged Vespasian as the new emperor the very next day, December 21st, 69. Finally, stability seemed possible.
But you mentioned the Civil War wasn't quite over yet. There's still trouble on the Rhine.
Right. While Vespasian had won in Italy, those powerful Rhine legions, Vitellius's original backers, they still hadn't accepted the new Flavian regime. And this internal Roman conflict got really complicated by the actions of the Batavi provincials, auxiliaries serving in the Roman army, led by a Batavian nobleman named Gaius Julius Civilis.
Okay, this sounds complex. You mentioned earlier there was some historical manipulation here by the Flavians about a revolt of the Batavi.
Yes, this is where it gets really fascinating, looking at how the winners write history. The new Flavian regime, with Mucianus probably pulling the strings politically back in Rome now, desperately needed to consolidate its image. They needed to be seen as the legitimate restorers of peace and order, not just another faction that won through civil war.
So how did they deal with the Rhine legions and the Batavi?
Well, they actually managed to get the Rhine legions to surrender and swear allegiance to Vespasian in AD 70, mostly through negotiation, promises of stability, maybe some strategic troop movements, rather than just crushing them in a huge battle.
Okay, that makes sense. But the Batavi part was embarrassing for them.
A profound embarrassment, yes. Because Julius Civilis and his Batavi auxiliaries had, at certain points during the chaos of 69, actually been fighting against the Vitellian legions on the Rhine. You could argue they were acting implicitly or even explicitly at times on behalf of the Flavian cause.
So Vespasian's side used non-Roman auxiliaries to fight Roman legions loyal to another Roman emperor.
That seems to be the uncomfortable truth, and the new regime simply could not allow the official history to record that. Relying on provincials, barbarians, in the eyes of many traditionalist senators to fight and defeat proper Roman legions, that would completely undermine the dignity of the empire and Vespasian's claim to be the unifier.
So they spun the story, they rewrote the history.
Precisely. The Flavian administration, almost certainly working with historians who relied on their patronage like Tacitus, whose histories are our main source for this,
Right.
they spun the entire incident. They reframed what Civilis and the Batavi did. Instead of portraying them as auxiliaries who helped defeat a Roman faction, Vitellius's, they depicted them as dangerous rebels who had launched their own revolt against Rome itself.
Making it seem like Vespasian's forces had to step in and put down a barbarian uprising.
Exactly. This spin allowed them to erase the awkward fact that Romans had used non-Romans to kill other Romans in a civil war. It reinforced Vespasian's image as the strong leader restoring legitimate Roman order against all threats, internal and external. It's a classic example of how victors control the narrative. And it reminds us that every detail we read about this year, especially maybe the extreme portrayals of Galba's cruelty or Vitellius's gluttony, needs to be seen through that potential lens of Flavian justification.
Okay, so let's try and connect all this back to the bigger picture then. The sheer importance of AD 69, it feels structural, doesn't it? Not just a chaotic year, but a year that changed the rules.
It absolutely is a pivotal moment. It marked the definitive end of ruling purely by bloodline. The Julio-Claudian legacy was finished, and it established the foundation for a new, durable dynasty, the Flavians. And crucially, the Flavians, Vespasian's family, they weren't old Roman aristocracy. They were from the Italian middle-class municipal background.
So his success proved something new.
It proved that practical administrative competence, military success, and pragmatism could trump ancient lineage. It opened the door for a different kind of emperor.
And Vespasian's ultimate success, compared to the other three that year, is underlined by one simple but really profound fact, isn't it?
Which is,
After 4 emperors died violently in less than 2 years, Vespasian actually consolidated the empire. He started massive building projects, like the Colosseum we still see today. He faced no really serious internal threats to his rule, and most tellingly, he died of natural causes in his bed in 79 AD. He actually solved the problem of imperial longevity, at least for his family.
he absolutely did. He seems to have mastered the key lessons that Galba, Otho, and Vitellius had failed to learn or failed to implement successfully. He secured the absolute loyalty of the legions, crucially ensuring they were adequately and regularly paid, unlike Galba. He imposed strict centralized discipline, and critically, he secured the economic resources, like that Egyptian grain supply, needed to sustain both the army's loyalty and the state's functions.
For our listeners who want to dive deeper into this incredibly chaotic period, the sources we have are actually quite vivid, aren't they? We rely on a fairly small but interconnected group of ancient writers.
Yeah, we really have to highlight Tacitus first. His work, The Histories, covers this period in just unmatched political and military detail. We have to remember, as we said, he was writing with likely Flavian perspectives influencing him, but he still gives us the deepest analysis of the military logistics, the shifting allegiances, the psychology of the armies, the political struggles back in Rome. It's indispensable.
And then you have Suetonius. He gives us all those juicy, often shocking personal details in his lives of the 12 Caesars. You know, the exact cost of Vitellius's dishes, the image of Galba's head on a pole. Suetonius is maybe less interested in grand political analysis and much more focused on the character flaws, the anecdotes, the scandals that bring these emperors, however briefly they ruled, to life.
Absolutely. And we shouldn't forget Plutarch. He wrote parallel lives, comparing Greek and Roman figures. He gives us detailed biographies specifically on the life of Galba and the life of Otho. These give us really valuable psychological insights into their motivations, their characters, particularly maybe Otho's rather surprising decision to commit suicide.
Right. And there's one more important context from outside the Roman heartland.
Yes, Josephus, the Jewish historian who wrote the Jewish War. His focus is obviously on the revolt in Judea, but because Vespasian and his son Titus were the Roman commanders there when this whole civil war kicked off, Josephus gives us this indispensable external perspective. He was essentially embedded with the Roman command in Palestine, so he provides a clear view of Vespasian's character, his military resources, and how the news from Italy was being received out there on the frontier.
Okay, so pulling it all together then, if there's one central takeaway from this whole deep dive into the year of the 4 emperors, what would you say it is?
I think it demonstrates brutally clearly that Roman stability, the peace of the empire, was no longer really reliant on the old constitutional traditions, the Senate's authority, or even necessarily the emperor's personal qualities beyond one thing. Satisfying the armed might of the state, the legions. It had become a marketplace for loyalty, not a dynasty based on birthright. Exactly. Galba's fatal flaw was thinking he could rule without paying the exorbitant price the Praetorians now demanded. Otho's tragedy, perhaps, was accepting the price, but being militarily defeated before he could consolidate his rule. And Vitellius's folly was squandering the empire's resources on personal excess instead of using them strategically to secure lasting loyalty and control.
And Vespasian.
Vespasian's ultimate genius was being the pragmatic, experienced general who understood the game. He secured the necessary resources, the grain from Egypt, the loyalty of the key legions, the finances, and he made sure the military felt invested in his success and the stability he represented. He set the standard, really, for how imperial transitions would often work or fail. for the next couple of centuries.
The truly devastating but absolutely defining period in Roman history. Before we wrap up, I want to leave you, our listener, with a final, maybe provocative thought, something to mull over about the ultimate consequence of this year of rapid military-driven succession.
Yeah, consider this. When the power of the emperor is clearly no longer derived primarily from tradition or law or divine right, but almost solely from the ability to command and, crucially, pay the army. And when rival armies, stationed hundreds of miles apart, can just declare their own commander's emperor whenever they feel like it.
Yep.
Did the Roman Empire, after AD 69, truly have a constitutional emperor in the old sense anymore?
Or had this year definitively transformed it? Had it become essentially a permanent, if often cleverly disguised, military dictatorship where legitimacy was really just a temporary truce based on which general had the strongest legions, the best location, and enough cash to keep them happy? That's the structural reality Vespasian inherited. And maybe he chose to manage it effectively rather than trying to dismantle it. A chilling thought about that evolution from republic to empire, and then maybe from empire to, effectively, a military state. Well, if this deep dive has grabbed you, we really do recommend looking up the geography and the specific legionary movements around those two battles at Bedriacum. They are the true bloody anchors of this incredibly revolutionary year.
Okay, when you hear the word bunker, what pops into your head? Probably images of, falling bombs, the Cold War, maybe massive concrete structures buried deep underground.
Right, exactly. They're sort of the ultimate engineered response to catastrophe, aren't they? More than just holes in the ground.
Yeah.
They really represent this massive investment in survival.
Yeah, absolutely. We're talking about these incredibly specialized, often huge structures designed to keep functioning when, well, everything on the surface is basically gone, pulverized.
They're really monuments in a way, monuments to human determination, planning, and some seriously ambitious engineering, like staggering stuff.
And that's precisely what we're going to unpack today. This is our deep dive into these engineered fortresses.
Yep. We're going to trace the history, starting with the word itself, which, trust me, has a wild backstory. Then we'll look at the different types, because they're not all the same.
And most importantly, maybe get into the nitty-gritty of the engineering. How do you actually build something designed to survive, forces 50 times greater than what takes down a skyscraper?
That's the core question, yeah. We've got a stack of sources here, and we're going to stick strictly to them to give you a really thorough picture of the structure, the purpose, the sometimes secret history of these places.
All right, so let's start with the basics, a definition. What is a bunker, technically speaking?
So technically, it's a defensive military fortification. Simple as that. Its whole job is protecting people and valuable stuff, materials, equipment from attacks, bombs, artillery, radiation, you name it.
And the key thing, the real identifier, compared to other fortifications.
Yeah.
It's about where it is, right?
Exactly. Placement is crucial. Bunkers are almost always underground. That's what really sets them apart from, say, a blockhouse. Blockhouses are usually mostly above ground, heavily fortified, but visible.
Gotcha. And historically, they were huge in the World Wars, the Cold War.
Indispensable. Used for everything, commanding control centers, storing weapons or supplies, deep underground, critical infrastructure.
But it wasn't just military. I was surprised to see in our sources that they have civilian uses too, using that same basic strength.
That's a really interesting point, that fundamental structural idea resisting massive pressure from a blast works just as well against certain natural disasters, specifically tornadoes.
Ah, okay. Because of the pressure difference.
Precisely. A well-built underground bunker doesn't really care why there's a massive pressure differential outside. Whether it's a bomb or a Force 5 tornado, it's designed to withstand it.
Okay, so before we get into the concrete and steel side of things, the word itself, bunker, you said the origin was wild. I think Hitler's bunker may be Gulf.
Oh, it's a fantastic linguistic journey. Get this. The word bunker starts out as a Scots word. Way back, 1758 is the first record we have, and it just meant a bench or a seat.
Yeah, seriously.
Seriously, a bench or a seat. And you can kind of see a link to the word bunk, like a sleeping berth on a ship or a train.
Okay, a seat, a bed, basic resting places. How on earth does that become a symbol of military defense? That seems like a huge leap.
Well, there's a possible deeper root that might bridge the gap a bit. It could be linked to an old Swedish word, bunk.
Bunker?
Yeah, bunk. And that word apparently referred to boards used to protect the cargo on a ship. So you go from sitting to sleeping to actively protecting something valuable inside an enclosure.
Ah, okay. That introduces protection, storage.
Yeah.
That makes more sense. So where did it go next in the 1800s?
It really leaned into that storage idea. In the 19th century, bunker became a pretty common word in England for everyday storage spots, like the coal store in your house or the place they kept fuel below decks on a steamship, a coal bunker, a fuel bunker.
Okay, so storage, mundane stuff. But then golf.
Yeah.
How does golf get involved?
Right. This is the crucial unexpected twist. Sometime in the mid to late 19th century, the word gets adopted by golf. And it meant exactly what it means today, that sand-filled hole designed to be a hazard, a bunker.
So coming into the 20th century, bunker means a coal cellar or a sand trap. Not exactly military hardware. How does it make that jump?
World War I is the catalyst. Global conflict changes everything, including language. So the English soldiers, they called their underground shelters dugouts. Pretty straightforward term.
Right.
But the Germans, they used the term bunker for their hardened, often concrete reinforced positions.
Ah, so the English first heard it used in that military sense from the enemy.
Exactly. It was the German word for their strong points. And our sources show that by World War II, the English military had adopted the term bunker, specifically when talking about German fortifications.
Initially just for German ones.
Yeah, at first. It covered everything from those big above-ground concrete blockhouses, the Hawk bunkers, to the smaller pillboxes, and of course the famous underground command centers, like the Führer bunker.
Wow. Can we pinpoint when it first appeared in English in that military sense?
We actually can. The first recorded use seems to be October 13th, 1939. It was in a report describing a Nazi field gun hidden in a cemented bunker on the Western Front. Notice the quotes around bunker. It was still seen as a foreign German term then.
That's fascinating. So how quickly did it lose the quotes and just become an English word?
It happened pretty fast, especially as the war progressed, and the Allies encountered similar structures built by, say, the Japanese in the Pacific. They started calling those bunkers, too. But the real sign it was fully integrated comes after the war.
How so?
By 1947, historians like Hugh Trevor Roper, writing about the end of the war in Berlin, just referred to Hitler's own bunker. No quotes, no explanation needed. The word had made the full journey from a Scottish bench to a ship's storage to a Gulf hazard to a German fortification and finally into standard English military vocabulary worldwide.
What a journey. Okay, so now we know the word. Let's get into the structures themselves. This is where it gets really cool, I think. Moving from one general term to all these specialized designs. They're not just holes, right? They're tailored.
Absolutely. The design is completely driven by the mission and the threat. Our sources break it down into 5 main types, and we start small, really, at the individual soldier level with the trench bunker.
Right, the basic protection in the trenches, World War I, early World War II stuff.
Exactly. Small, concrete structures, usually partly dug in, but incredibly important. They were part of the trench system itself, offering way better protection than just an open ditch. You got cover from shells bursting overhead, from shrapnel bombs, and just shelter from the weather, which was huge for morale.
Did they ever have to compromise on that protection for, like, practical reasons?
Yeah.
To actually fight back?
Oh, yeah. That's a constant theme in bunker design, the trade-off between protection and function. Some trench bunkers actually had partially open tops.
Open tucks. Seems counterintuitive.
It does, but it was deliberate. It let the soldiers fire weapons like mortars or maybe even anti-aircraft guns upwards out of the bunker. So you sacrifice some overhead protection for the ability to shoot back effectively in certain directions.
Okay, makes sense. Now, scaling up significantly.
Yeah.
Artillery bunkers. These sound like the big boys, the pre-Cold War giants.
They really were. Huge, complex systems, especially for coastal artillery. You know, those massive guns defending harbors and coastlines. Those guns were enormous investments.
The bunker protected the gun and the crew.
Both, and the ammunition, too. Protecting the crew was vital, obviously. Protecting the ammo was critical to prevent catastrophic secondary explosions if the bunker got hit. And yeah, sometimes they protected the guns themselves within the concrete structure.
But putting a giant gun inside a concrete box must limit where it can shoot, right? That trade-off again.
Absolutely. It severely restricted the field of fire. You couldn't just swing the gun around 360 degrees, but The thinking was sometimes just keeping the gun operational, even with limited firing arcs, after taking a hit was more important than having a wider field of fire that might be knocked out immediately.
These things must have been enormous. What kind of scale are we talking about?
Truly massive.
Yeah.
The sources mention the battery taught in northern France, a German coastal gun battery. The walls there were up to 3.5 meters thick.
3.5 meters. That's almost 11 feet of concrete and steel.
Yep. Designed to withstand naval shells, heavy bombers, just immense. And they built totally underground bunkers just to house the complex machinery for weapons like the V3 cannon. The bunker was the weapons system, in a way.
Which leads us nicely into the next type, industrial bunkers. Shifting from direct combat to protecting the stuff behind the lines, the factories, the resources.
Exactly. Germany, especially in WWII, facing constant bombing raids, built these to keep vital industries running. It wasn't about fighting, it was about continuity. Protecting mining operations, food storage, raw materials, data archives, sometimes even living quarters for essential workers.
And this type still exists today.
Right.
Not for war necessarily, but for handling dangerous stuff.
Absolutely. Modern industrial bunkers are critical for safety. Think about control rooms for rocket engine testing or experiments involving high explosives. You need that hardened structure. Also, for storing hazardous materials, radioactive waste, volatile chemicals, even in purely commercial settings that contain accidents.
Containing accidents. That brings us to a really specific type. Munitions storage bunkers. Here, the goal isn't stopping something getting in, but stopping something accidentally getting out.
That's the key difference, yes. Securely storing bombs, shells, explosives, and critically, if one goes off accidentally, containing that explosion, preventing it from setting off the neighboring munitions or scattering debris.
And they often have that distinctive igloo shape, right? Why is that?
The igloo, or arch shape, is really effective at directing the blast pressure outwards and upwards, and they're very often built into hillsides.
Using the earth itself.
Exactly. The surrounding earth provides extra mass, extra containment, helping to absorb the shock wave and fragments. It's a very efficient design.
And the ultimate example of containing an internal accident has to be the gravel Goldie. That sounds like something out of science fiction.
It's an amazing piece of safety engineering, isn't it? A gravel Goldie is designed for one very specific, very scary scenario, an accidental explosion while assembling or disassembling a nuclear weapon.
Wow. So how does it work?
If there's an accident, a conventional explosion involving the non-nuclear parts, the structure is designed to contain the blast. But crucially, it's filled with gravel. The idea is that the radioactive materials released in the accident get trapped within that gravel fill inside the bunker, preventing them from spreading into the environment.
Incredible. So they're basically filters as well as blast walls. Where would you find these?
They're a standard safety feature at facilities in the U.S. and the U.K. that handle nuclear warhead components. Like the Pantex plant in Texas, they have, I think the source said 12 of them. It's all about preventing a localized accident from becoming a widespread radiological disaster.
A bunker designed to protect the world from what's inside it. That's quite a concept. Okay, last type. Personal bunkers. Bringing it down to the individual or family level.
Right. These are purpose-built for private protection. Sometimes integrated into a house design, maybe as a reinforced basement room or even a bathroom. Materials vary. Fiber-reinforced plastic shells are common. They often use earth arching again for strength, burying the structure so the soil provides compression. And that soil layer, the overburden, also provides significant radiation shielding.
But if you're burying a big plastic shell, especially somewhere with a high water table, doesn't it just want to pop back up like a boat?
That's a huge engineering challenge. Flotation is a major issue. To stop the shelter literally floating out of the ground, they often design them with a skirt.
A skirt?
Yeah, like a flange or lip around the base. The weight of the soil packed on top of that skirt holds the whole structure down, anchoring it against the upward pressure from groundwater. Pretty clever, really.
In this category, it's kind of gone high-end now, hasn't it? The luxury bunker phenomenon.
Oh, absolutely. It's moved way beyond basic survival for some people, driven by, anxieties about political instability, social collapse, whatever. Super wealthy individuals are commissioning these vast underground complexes. We're talking massive energy storage, redundant life support, but also things like operating theaters.
Operating theater.
Yep. And bowling alleys, according to our source.
Bowling alleys underground.
Okay.
Survival has definitely been redefined there.
Survival with amenities, let's say.
Right. So connecting all these types, The engineering needed is just immense. We're talking about physics at extremes the everyday world just doesn't see.
Exactly. It's about forcing materials to withstand incredible forces. Let's look at blast protection first. How does concrete actually stop a bomb blast from killing you?
Yeah, how does that work?
The main goal is to deflect and dissipate that shockwave. You need to prevent the sudden, massive pressure change inside the bunker because that's what causes lethal injuries to ears, lungs, internal organs. To get a sense of scale, think about overpressure. Your average building, like a house or an office, it'll collapse under about 21 kilopascals of overpressure. That's only around 3 psi. Seems tiny.
3 CS,
Yeah.
that's it. Wow, so bunkers need to be much, much stronger.
Orders of magnitude stronger. We're talking structures routinely designed to withstand over 1,000 kilopascals. That's 150 psi, or 10 bar.
50 times stronger than a normal building.
At least, that's the kind of resistance you need to have a decent chance of surviving anything less than a direct hit from a specialized weapon.
And how do they achieve that? What are they typically made of?
The gold standard is heavily steel-reinforced concrete, usually formed into a vault or an arch shape and buried. The arch is really effective because it transfers the force outwards into the surrounding earth using compression.
But what if you don't have the resources for a massive concrete vault? You mentioned expedient options.
Right. Sometimes you can use existing underground structures, big sewage pipes, subway tunnels. They already have some inherent strength because they're designed to resist pressure from the surrounding earth.
And improvised ones.
For improvised shelters, you can use earth itself. The technique involves digging a trench, putting some kind of flexible frame inside, maybe thin wood bent into an arch covering it with something waterproof, and then carefully packing 1 or 2 meters of soil on top. The strength comes from the compacted earth arch, not really the frame itself.
Okay, that handles air blast, but what about ground shock? If a bomb penetrates deep or hits nearby, the ground itself shakes violently.
Ground shock is a huge problem for deep bunkers. A big explosion nearby can make the bunker's own walls and floor jump several centimeters in just milliseconds. That sudden, violent movement can kill everyone inside, even if the bunker structure itself doesn't actually break.
So the bunker survives, but the people inside are thrown against the walls.
Essentially, yes, lethally. So how do you protect them? You basically build a bunker inside the bunker. The critical facilities, the command center, the living quarters, they're built as a separate internal structure that sits on massive springs or shock absorbers.
Seriously.
Yeah, huge shock-absorbing systems. It mechanically decouples the inner box from the outer shell. So the outer concrete vault might heave and shake from the ground shock, but the inner room, where people are, stays relatively stable. It isolates them from that violent motion.
That is incredible. What about nuclear threats? That adds radiation and under pressure. What's that?
Right. Nuclear adds complexity. You've got the initial blast wave, the heat, the radiation, and then this underpressure effect. After the main shock wave passes, there's a period of lower than normal pressure, kind of suction effect, that lasts for several seconds.
So the bunker has to resist being pushed in, then pulled out.
Sort of, yeah. But the good news is the radiation shielding comes from the same thing that provides blast protection. Mass. Lots of earth overburden, thick concrete walls. They block radiation pretty effectively. And the underpressure, while significant, is generally only about 1/3 of the initial overpressure. So if you've designed for the big hit, you can usually handle the pullback.
Okay, let's talk about keeping people alive inside for potentially long periods. The weak points are always the openings, right? Doors, vents.
Absolutely. The door is the classic vulnerability. It has to be just as strong as the walls, if not stronger. Modern bunkers use heavy vault doors, usually steel, set in very strong frames.
I saw something interesting in the notes. Sometimes they use thick wood. That seems less strong than steel.
It does, but wood has an advantage against intense heat or fire. Steel can melt or warp, losing its seal. Very thick wood, on the other hand, tends to char on the surface. That char layer actually insulates the wood underneath, helping it maintain structural integrity for longer in a fire scenario.
Huh. Clever. And how do you stop the blast wave just ripping the door off its hinges?
For doors on the surface, the design is critical. The edge of the door has to be countersunk, meaning it fits deeply into the frame, not just sitting against it. This prevents the blast wave from getting a purchase on the edge and peeling the door open or shearing the bolts.
And you always want more than one way out, presumably.
Ideally, yes. Redundancy is key. 2 doors, minimum, if possible. And often, to save on digging, those access shafts double as ventilation shafts.
Ah, ventilation. Crucial if you're sealed inside. You'd run out of air or overheat pretty fast.
Very fast. People generate a lot of heat and carbon dioxide.
Oh,
Without massive amounts of ventilation or air conditioning, a sealed bunker quickly becomes lethal just from the internal environment.
and in wartime, you can't rely on the power grid for fans or AC.
Exactly. So manual backup is essential. Manually operated ventilators were a standard feature.
Was there a particularly good design for that? Something efficient?
Yes, the sources mention the Kearney air pump. It was designed to be very efficient, using a large diaphragm or bellows system that could move a lot of air with relatively little human effort. Vital for survival when the power's out.
Okay, so you have vents, but how do you stop the blast wave coming through the vents?
Blast valves, that's their job. These are clever devices. They stay open normally, letting air flow in and out, but the instant a pressure wave hits them, they slam shut automatically.
Protecting the inside from the overpressure.
Exactly. And there were even expedient versions. Our sources mention using old, flat rubber tire treads.
Tire treads.
Yeah, nailed or bolted over the vent opening inside a strong frame. Normally, they'd hang loose, letting air pass, but a shock wave would instantly slap them flat against the frame, creating a temporary seal. Simple, but apparently effective.
Ingenious. Okay, we've got the science down. Let's talk famous examples. Where can we see this engineering in the real world? The interwar period was big for fixed fortifications, right?
Huge. It was kind of the golden age of believing concrete could solve all security problems. You had the massive Maginot Line in France, of course, the Czechoslovak border fortifications built against Germany, Fort Ibn Email in Belgium, a fortress considered state-of-the-art.
Italy, too?
Yep, the Alpine Wall on their northern border.
Mhm.
All these massive linear defenses. Ultimately, they didn't stop mobile warfare, but the scale of construction was incredible.
And the German V-weapon sites were basically giant industrial bunkers themselves.
Yeah, totally. Middlework, the undergrain factory, La Coupole, and the blockhouse Dipperlech in France. These weren't just shelters, they were hardened factories designed to withstand bombing and keep producing advanced weapons. Monumental engineering.
Then the Cold War shifts everything. It's not about borders anymore. It's about surviving nuclear Armageddon, ensuring the government continues.
Exactly. Continuity of government became the driving force. This led to the deepest, most secret bunkers ever. In the U.S., you have iconic places like Cheyenne Mountain in Colorado, Site R Raven Rock Mountain Complex, and the amazing Greenbrier facility hidden under a luxury resort meant for Congress.
And other countries did the same.
Oh, yes. The UK had Burlington, Canada had the Diefenbunker. These weren't just shelters, they were designed as underground command centers, self-sufficient for months, potentially housing thousands of key personnel to run the country after an attack.
And this idea of going underground became a national strategy in some places, right?
Yeah.
Not just for the elite.
Definitely. Look at Switzerland, probably the most bunkered country on Earth. Since 1963, they've had a law requiring nuclear shelters in all new buildings. Combine that with their military's National Redoubt Plan, the country is honeycombed with shelters.
And some of those Swiss bunkers have a new life now.
Yeah, it's fascinating. With the Cold War over, many are obsolete for defense. So places like the Sasso San Gottardo Museum are now tourist sites. Some have even been converted into hotels. You can literally sleep in a Cold War bunker.
Wild. What about the Soviets?
They leveraged their existing infrastructure, the Moscow Metro, the Kyiv Metro, famously deep subway systems. They were explicitly designed to double as massive public nuclear shelters. China did similar things with Beijing's underground city and Project 131. It was a global phenomenon among the major powers.
And then there's Albania,
Yeah.
which is just extreme.
Albania under Enver Hoxha is a unique case. His paranoia about invasion led him to build hundreds of thousands, literally, of small concrete bunkers all over the country. The landscape is still dotted with them, a very visible legacy of fear.
And back in the U.S., the ultimate symbol is right under the White House.
The Presidential Emergency Operations Center, the PEOC, under the East Wing. It's the secure command post and shelter for the president. Ensures that, in a crisis, the head of state survives and can maintain command. It's the pinnacle of continuity planning.
Okay, so we've talked about incredible strengths, 11-foot walls, buildings on springs, vault doors, but they're not invincible, are they? How do you actually defeat a bunker?
No, nothing is invincible. That offense-defense race never stops. The most straightforward way is brute force. Incredibly powerful conventional bombs or specialized bunker buster munitions designed to penetrate deep underground before exploding. They try to overwhelm the structure.
And for smaller ones? pillboxes and such.
Sometimes surprisingly low-tech methods work. Against the crew inside a small pillbox, flamethrowers were tragically effective. But the universal vulnerability for any complex bunker, big or small.
The doors and vents again, the access points.
Exactly. The sources really emphasize this. You might not be able to crack the main structure, but if you can attack and seal off the exits, the ventilation shafts, you trap the crew inside, the bunker becomes useless, neutralized, you can just bypass it. The strongest fortress can be defeated by blocking its doors.
That's a powerful point. Wow, this has been quite the journey. From a Scottish bench to underground bowling alleys, exploring the engineering needed to resist forces 50 times normal. It's incredible stuff.
It really shows that constant push and pull, doesn't it? Between the technology of defense and the technology of offense, the bunker is like the ultimate physical statement of wanting to survive no matter what. But even that hits fundamental limits, like needing a way in and out.
So what's the big takeaway for us listening to all this?
Well, we've talked about building incredible strength, designing for survival against overwhelming force, but we also found that even the most hardened bunkers, those 3.5-meter thick walls, are ultimately vulnerable at their necessary weak points, the access points, the doors, the vents. So maybe the final thought for you, the listener, is this. When you think about defense, whether it's personal safety or national security, does true security lie more in preventing the attack in the first place? Or does it lie in constantly trying to build thicker walls around those unavoidable vulnerabilities? Where's the better investment?